Hello and happy Super Bowl Sunday. Go Chiefs. I'm Abby Francisco, and this is my presentation on the fate of lactate. So I'd like to briefly go over very quickly the ATP production from glucose, and then we'll start right into the lactate pathway. So if you remember a couple weeks ago, ATP production from glucose starts with one glucose, and through glycolysis, it produces 2 net ATP and 2 NADH. Now that one glucose yields 2 pyruvate. And when oxygen is present, it converts to acetyl-CoA, and then after it goes through the Krebs cycle or citric acid cycle. And when oxygen is not present, we'll go through the lactate pathway, which is our topic for this week. So now we're here in the beginning of the lactate pathway. So with no oxygen present, pyruvate goes through lactic acid fermentation, using lactate dehydrogenase. Now what yields is some lactic acid, which actually quickly dissolves into lactate and hydrogen ions. Now this lactate and hydrogen ions get sent into the bloodstream over here, which is buffered by a bicarbonate, which we'll go into later, and converted into glucose. So let's take it back just a little bit with the lactate through the bloodstream getting transported to the liver. Now lactate will convert into pyruvate through lactate dehydrogenase, and from there pyruvate will convert into glucose via gluconeogenesis. Now this process is quite expensive, requiring 6 ATP and yielding 2 NAD pluses, and this is something that we'll cover a little bit later. So you have pyruvate converting into glucose, and glucose is then sent back into the bloodstream to the same muscle or a different muscle, or it can be stored in the form of glycogen. Okay, so what affects the lactate pathway? One of the things that does is exercise intensity. So there are a couple things to just keep in the back of your mind. One is the relationship between exercise intensity, and lactate production, there's a direct relationship. So as intensity increases, lactate production increases as well. Now that other tidbit of information is the term lactate threshold. And in this graph here, this chart here, you'll see about where that lactate threshold is, which is about 1 millimole of liter of blood lactate. And what that is during exercise, lactate begins to accumulate. And at this point, 1 millimole of liter, that's where it starts to accumulate. So in low to moderate exercise intensities, lactate production doesn't quite surpass clearance. We're able to clear it as fast as we are producing it. So the individual is relatively stable. Now in higher intensities, lactate buildup accumulates. And another term that's pretty important is OBLA, or the onset of blood lactate accumulation. So now you'll see in this point right here, that is where we start that OBLA, or when we're getting greater than 4.0 millimoles per liter of blood lactate. Now what happens here is there's an increase of hydrogen ions in the bloodstream, which again we'll go back to later, as it decreases pH, meaning our blood becomes a little bit more acidic. Now, trading adaptations. So if you take the concept of OBLA and that blood lactate accumulation, and you take a trained individual versus an untrained individual, you'll see a couple differences. Now the trained individuals will experience OBLA at a greater exercise intensity than that of an untrained individual. So if you look at this graph here, that lactate threshold is occurring at about 75 VO2 max, whereas in the untrained individual, it occurs at about 50. Okay, again, the trained individual has a greater capacity for exercise intensity. Additionally, trained individuals have a quicker lactate turnover or conversion, meaning they're able to convert lactate back into glucose quicker than that of an untrained individual. And lastly, trained individuals have greater intramuscular glycogen storage. Now what this means is with greater glycogen storage, there is more glucose, and with more glucose available, there is more lactate production through glycolysis. So you're able to contribute more to that anaerobic glycolysis if you're considering a more trained individual. So the key points of these two slides here, exercise intensity and training adaptations, are as intensity increases, so does lactate production. And in trained individuals, they will experience OBLA, or that onset of blood lactate accumulation, at a greater exercise intensity than that of an untrained individual. So what are some consequences of lactate accumulation? What happens here is the lactate production is greater than the lactate clearance. So there is an increase in hydrogen ions, which decreases blood pH, making it more acidic, and that byproduct is carbon dioxide, so carbon dioxide increases as well. So what happens here is, like we mentioned, pH goes down, and when it gets lower than 7.0, which is our neutral or alkaline, we start to experience some signs and symptoms such as nausea, headache, dizziness, soreness, pain in the active muscles, which I'm sure most of us have felt. You know, if we hit the gym a little bit too hard, ran a little bit too much, and the next day you started to feel like your legs were going to fall off. So it is our muscles kind of signaling rest or that you need a break. There is a potential of cessation of exercise. So molecularly, if you remember when we were talking about the process of pyruvate converting back into glucose through gluconeogenesis, that was an expensive process. It required 6 ATP, and glycolysis only yields 2 ATP. So your net total is -4. You're in the -4 ATP, and eventually you will have to cease exercise as you're going to continue being in the negative. Lactate does get buffered in the bloodstream, as we mentioned that bicarbonate buffer earlier. There's a couple ways, one of which being oxygen consumption, and it does increase lactate clearance. As we use more aerobic glycolysis, it allows the clearing of lactate and is then filtered out through liver and produces glucose. And then again, that plasma bicarbonate also helps to clear out hydrogen ion buildup in the blood, and then carbon dioxide is a byproduct which eventually gets exhaled out. Now, can lactate be used as a metabolite? It can indirectly be used as a metabolite via gluconeogenesis. Now, if you remember, it is indirectly transferred into the liver because first we have that lactic acid, which dissolves into lactate and hydrogen ions, and then it's converted into glucose via gluconeogenesis, then transferred into muscle, where then it can be metabolized and used as a fuel source. It can also be shuttled to other muscles and converted into pyruvate. Now, if oxygen is present, like we mentioned in the first slide, as well as a couple weeks ago, it will convert into acetyl-CoA and then carry on to the Krebs cycle, again producing ATP. So both of these converting into pyruvate and if oxygen present, converting into acetyl-CoA and going to the Krebs cycle, both produce ATP. And lastly, we have the difference between lactate and lactic acid. Both terms are often used interchangeably, but they're actually two different entities. Lactic acid is really just the conjugate base of lactate with an intramolecular hydrogen bond. So it's right here. It is more acidic, having a lower pH or creating a lower pH, and it is formed by combining two hydrogens with pyruvate. Lactate can be transported into the liver via the bloodstream, where lactic acid cannot. If you remember, it has to dissolve into the hydrogen ions before getting transported to the liver. And it is produced during exercise. Lactate is produced during exercise, and it is the final product of anaerobic glycolysis and result of lactic acid fermentation. Thank you.